Radar guns. What are they? Radar guns are handheld devices used by traffic police to estimate the speed of a passing vehicle. How do they work? A radar gun works by transmitting electromagnetic energy, in this case in the form of radio waves, into the environment and detecting the energy reflected by objects. The radar gun picks up this echo and calculates its Doppler shift. So, as you can see, this picture demonstrates the use of the radar gun. The black lines are the radar waves, and the dotted blue lines are the reflected waves off of the red car. So, put in more simple terms, the radar gun shoots the wave at the moving object and detects the speed of the object by measuring the frequency of the wave that is reflected back from the object. And there's another image there to demonstrate what's going on.
Just as a side note, as we already said, a radar gun uses radio waves, and these radio waves are transverse waves, meaning their wave structure is perpendicular to the medium they are traveling through. Radio waves have a frequency ranging from 3000 Hz to 3 times 10 to the 11th power Hz. A radar gun is based on the Doppler effect, which describes the increasing frequency of waves on a stationary observer as the moving source heads towards the observer, and likewise a decrease in frequency as the source moves away. The frequency shift that this radar gun picks up from the echo is directly proportional to the velocity of the moving object that reflects the echo. So, here is an equation of the Doppler effect, where f of I equals to the frequency sent out by the radar gun to the object, and f of s equals to the frequency reflected back by the vehicle. V equals to the velocity of sound, v of s equals to the velocity of the vehicle, and v of I equals to the velocity of the radar gun. When an object is still, f of I equals to f of s. However, when an object is moving towards the radar, f of I is less than f of s. This is when frequency is compressed, and therefore the frequency of the wave reflected back is increased. On the other hand, when an object is moving away from the radar, f of I is greater than f of s. And this is where frequency is stretched out, and therefore the frequency of the wave reflected back is decreased. To put this concept in more simpler term, we can look at this illustration on the screen. The first two rows of illustration represents a still object on the right, which is the car, and this is where the frequency of the wave that is shot out by the gun equals to the frequency of the wave that is reflected by the car to the radar gun. However, you can see on the third row where the car is moving towards the radar gun. And this is where the frequency of the wave reflected back is compressed and the frequency increases. On the other hand, when the car is moving away from the radar gun, which is shown on the fourth row, the frequency of the wave reflected back is stretched out, and therefore the frequency is decreased. The waves that are reflected back are detected by the radar guns, which determines and calculates the velocity of the object.